Welcome to this course Applied Thermodynamics. We are in the internal combustion engine module 3. Till date we have discussed about 6 lectures. Today we are in the 7th lecture, that is combustion phenomena in engines, and in fact this is the one of the most vital part of engine study. So, in this combustion phenomena we are going to discuss about the concept of homogeneous mixture combustion, heterogeneous mixture combustion, and how these two combination or how these two concepts are utilized for studying the combustion mechanism in SI engine and CI engines. This is the main philosophy or topics of discussion for today. So, let us talk about something on homogeneous mixture combustions. So, ideally when you look at the combustion mechanism in engine, it is very complex and it should be understood through correlation of various engine parameters such as pressure, temperature, type of fuel, knock characteristics, engine speeds. The conditions that is necessary for combustions are the presence of combustible mixture. For combustible mixture I mean, in fact we studied last class, we require fuel and we also require oxidizer, and this mixture will give you the combustible mixture, and suitable composition of this combustible mixture will help us in igniting the fuel. Now, this ignition process can have two ways. One is fuel can self ignite, or we have to manually ignite the fuel using some mechanisms. So, for this combustible mixture preparation we have two concepts. One is homogeneous mixture concept, other is heterogeneous mixture concepts, and with this mixture is nothing but fuel, vapor and air. So, let us briefly discuss about what does this homogeneous air fuel mixture and heterogeneous air fuel mixture. So, when you say homogeneous air fuel mixture, we feel that air and fuel are mixed or pre-mixed and they are compressed in the engine cylinder, and after the compressions the charge needs to be ignited externally by means of a spark plug. The other ways of looking at the heterogeneous combustion is that instead of the fuel air charge in the cylinder, we have only air in the cylinder, and this air is already compressed, and in this compression process the pressure and temperature have already rise to a certain level, and now at this elevated pressure and temperature when the fuel is injected, it is going to self ignite, and after this combustion the flame needs to be developed and this flame tries to propagate. So, this is how the concept of homogeneous and heterogeneous combustion concept in the engines. Now, when you let us start first with homogeneous combustions. As I mentioned, this is mainly used in SI engines. Mixture is prepared using a carburetor and a spark plug is used to ignite the charge. After the combustion, a flame front is going to be generated, and this flame front is trying to propagate within the combustible mixtures. So, when the flame front moves in the engine cylinder, it is moves at certain velocity, and that velocity we call as a flame velocity, and during its motion it caused an enhanced heat transfer and diffusion of burning fuel molecules. As a result, the unburnt mixtures gets the feel of the burnt gases for its ignition. There are some other concepts of homogeneous combustion. is that typically the homogeneous mixture with equivalence ratio close to stoichiometric value, this flame speed is noted to be about 0.4 meter per second, but the maximum flame speed it is possible when the equivalence ratio is 1.1 to 1.2, that means fuel is rich, that is mainly in SI engines. But when the flame front speed drops to a very low value or low equivalence ratio, then heat loss from the combustion zone becomes equal to the heat release due to the combustion. So, that means flame is extinguished and it does not have any strength to move further. So, in order to avoid this fact, many times we create artificial turbulence in the cylinder. So, for proper air movement and mixture gets mixed properly with a particular value of equivalence ratio, which is good for generation of the flame and its propagation. Now, something on heterogeneous combustions, and this is mainly used when we are using in the CI engine. Here the entire idea is that the engine cylinder is filled with compressed air, and on this compressed air the fuel is injected. When the fuel is injected, this fuel tries to self ignite, and when it fuel tries to self ignite, and in this process it tries to spread within this engine cylinder. So, when the here also flame front is developed, but this flame front generation is a localized phenomena, because this particular flame front is generated when the charge feels that it has sufficient quantity of fuel and air mixture for flame generation, and locally it is homogeneous. But however, when it spreads, it moves with certain velocity, and side by side it tries to ignite the all subsequent layers of fuel air mixture. When with heterogeneous mixture, we have a varying equivalence ratio 1 to 1.2 in the local zone, that means it is locally homogeneous. The ignition starts with fuel rich zone, and the flame is produced by this process helps to burn the any adjoining zones where the mixture is lean. In the zones when the mixture is rich, combustion occurs because high temperature is produced due to the initiation of combustion. So, this particular concept is completely different than that of SI engine. Now, let us move to one by one the first mechanism, which is combustion in SI engine, and in this combustion mechanism we are now going to study what are the different concepts involved when we look at the combustion process, in particular in SI engines. So, there are three broad categories or broad regions in the combustion process. First is ignition which is done through spark plug, and after the ignition immediately there is a flame development for certain time period. Then after the flame gets developed, it tries to propagate. So, we call this as a flame propagation, and the flame termination, that means when the flame has to terminate at a particular time or instant when all the charge is burnt completely. So, these three sequence of events that happens in SI engine we are going to discuss today. So, let us see that if you look at the engine cylinder, the entire fresh air and fuel mixture is squeezed in an engine cylinder after compression, and if you can imagine there are different layers of region like 1, 2, 3, 4, we can divide this engine cylinder, and what happens is that already the entire charge is compressed. Now, it is ready for ignition. So, this ignition is done through spark plug. When it ignites, so first layer of the charge gets burnt, and side by side when it moves, as a result a flame is generated. So, once region 1 is completely burnt, so this flame tries to squeeze the rest of the mixture into a very small volume when it propagates. So, in this process rest of the volumes in the region 2, 3, 4 gets burnt. So, and the flame terminates when the entire charge in the all the region 1, 2, 3, 4 is burnt, and during the flame motion it should be noted that at the beginning of combustion process the flame propagation or flame moves at a faster rate, but towards the end of the cylinder the rate of reaction is small because there is not enough charge to be burnt, and side by side there is a wall, what you can view it as a wall or piston face just after the region 4, where the entire heat is going to be penetrated to the walls of the piston. So, that means the heat gets consumed. So, this charge does not get sufficient quantity of heat, number 1. Number 2, there is not enough quantity of charge is left. So, one point of time when the entire charge is burnt, the flame gets extinguished. So, at that point of time we call it a flame termination. So, in this sequence of events there are many things that are going to happen. Now, we will discuss one by one. So, first thing what we are entire process, that is from ignition to flame development to flame propagation to flame termination, at the end of the day what you see is a constant volume process. So, this constant volume process we have ignition, and that we represent a characteristics diagram what we call as pressure crank angle diagram. So, in this pressure crank angle diagram, in our earlier cases we normally view that pressure crank angle diagram in particular we are looking at the compression process, we are looking at the expansion process, but here we will very specifically focus our attention that what happens to the charge immediately after the ignition. So, first of all when you ignite, after some time combustion starts and there is a flame propagation period. During the flame propagation period entire charge gets burnt completely, but so the pressure rises very sharply. So, in the beginning the rise is small, but after some time the rise is very fast because that is during the flame propagation period. And just after the TDC, that means the maximum pressure we can see when the just after the TDC, and once entire charge is burnt, that means entire 1, 2, 3, 4 region charge is burnt, entire charge is burnt, then the piston is about to move in the return stroke. That means entire the force generated due to rise in the pressure is imparted on the piston's face. So, as a result piston starts moving in the expansion stroke. So, this is how we call this as a pressure crank angle diagram, and the experimental data shows that maximum pressure rise occurs 5 to 10 degree after TDC. The ignition and flame development. So, let us see that in the different zones or different sequence what are the features that are involved. So, the first case is ignition and flame development. So, ideally during this period we say that only 5% of the charge is burnt, and here there is no noticeable or useful work is produced. And in this period the combustion is initiated by electric discharge and through a spark plug, and somewhere it is done 10 to 30 degree before TDC, somewhere in this region. So, this particular is about 10 to 30 degree. Now, how this discharge happens? This discharge happens through a plasma discharge, and which is created across the electrodes of the spark plug, and in this process when this fuel is ignited the combustion spreads outwards, and through this process when the discharge happens we normally give a voltage potential about 25 to 40 kilovolts, but for a very small time period of 10 to the power minus 9 seconds, and during this process we have a very high current about 200 amperes. So, imagine that at this voltage 25 to 40 volt and 200 amperes, we expect a peak temperature about 60,000 Kelvin, but it is lasting period is very small, close to a nanoseconds. But we can see that the average temperature that can be recorded is about 6000 degree Kelvin, but for even that also for a 1 millisecond period. And another significant is that during this ignition and flame development period, we actually supply a very small amount of energy, which is about 0.2 megajoule for to ignite the self sustaining combustion. The maximum voltage that can be of, as I mentioned, is about 40,000 volt, current about 200 amperes, and the total energy delivered during the discharge period is about 30 to 50 millijoule. So, as you can see in this figure, we have a breakdown voltage or phase, and during the small time scale of 10 to the power minus 9 second, we feel that about 200 amperes of current is felt, and we spend in energy about 30 to 50 millijoule. So, after that period is over, next period is the flame propagation, and in fact, it is the most crucial period for SI engine combustion, because here about 80 to 90% of the fuel is burnt, and most of the work or substantial work on the or force is being produced during this period. And when the flame front is generated, we need to enhance its speed. So, to do that, we have to create some kind of artificial turbulence, swirl or any other mechanism, so that we can increase the flame speed. So, now when the flame speed is increased, then it is more likely that it will burn most of the fuel mixture. Now, when the fuel air is burnt, and the flame front becomes hotter, and it tries to compress the unburned gas, and side by side it also generates lot of temperatures which is behind the flame front. The another features are that I mentioned earlier that if you look at this particular figure, the mass of air fuel mixture is distributed as the spark plug is fired at the start of combustions. The flame front moves across the chamber, unburned mixture in front of the flame is compressed to a very small volume, and the flame front continues to compress the unburned mixture with increase in the pressure and temperature, and this compression raises the temperature of the gas above its self ignition temperature. Then this you can have knock. So, here another important feature I just want to mention, that when the flame front tries to moves, so ideally the flame front should burn all the charge in the cylinder, but if it does not happen, why it does not happen? Because the compression of the charge would have created very high temperature, so that the charge in the region 4 gets burnt first. So, when it gets burnt, so it tries to give a retarding motion to the flame front. So, it does not, it means it gives a resistance to the flame front to move, propagate further. So, if this happens, we can have that the knocking can happen. So, it will create a unbalanced force on the piston face, and this should be avoided. At any point of time, the compression should not raise the temperature above the SIT of the means self ignition temperature of the fuel. Another important aspect of flame propagation is that we need to look that how much charge we are going to burn. Now, when they are burnt, how they occupy the space in the engine cylinder. So, this particular picture shows that when we are burning about 30% of the charge. So, 30% of the charge means we are somewhere here. At that point of time, we can see that it occupies about 60% of the volume, and subsequently they compress about rest of the 70% of the mixture which is not burnt, and that is occupied in the 40% of the volume. So, in this process, so their design is that the flame plant should move at certain velocity, that it should burn in a very sequential manner, and every instant only there are certain quantities of the fuel needs to be burnt. So, that we do not have any unwanted expectations of pressure rise within the engine cylinder. So, this is how the significance of this particular plot is all about. And moreover, we need to ensure that during the flame propagation period, maximum charge about 80 to 90% should be burnt. Some of the other features that are I can say that the when you burn about 80 to 90% of the charge, so the useful work is going to be produced. Another important aspect is that as the burnt gases strength increases, so the flame front becomes hotter and hotter, and thereby it gives reasonable amount of pressure to the unburnt gases. As a result, the unburnt gases gets the feel of the heating and tries to burn. So, next aspect about this flame propagation is knock. So, I mentioned some of the concept that knock can happen in the region 4 or the last regions, or which is close to the piston face. Now, when you see this knock, what we actually see? We are looking at unwanted rise in the pressure pulses in the engine cylinder or P theta diagram. So, what you can see is that during the expansion stroke, it should ideally it should be the P theta diagram should be smooth, but it is now filled with unwanted pressure pulses, because the fuel has self ignited, and this is a very crucial factor which needs to be accounted. So, for that it has been found out from experiments that 2/3 of the fuel air mixture should be burnt at TDC, and almost completely about 15 degree after TDC, so that maximum pressure and temperature can occur 5 to 10 degree after TDC. So, this condition is to be ensured, and the maximum pressure rise is about 240 kilopascal per degree of engine rotations for smooth transfer of force on the piston face. So, these two aspects is very vital to ensure quantitatively such that we get a very smooth combustion or normal combustion as shown in this particular figure. Another look of flame propagation, many people say that how you are going to enhance the flame speed. So, there are ways to create a higher turbulence, there are ways to create or increase the engine speed, and there are ways that we can also think about the richness or of the fuel air mixture. So, all these things needs to be addressed by in this particular figure. What it says is that how the flame front varies, flame speed varies with air fuel ratio. So, as you can see, for SI engines, when we are going towards lean side, the flame speed drops. On the other hand, if we are increasing the speed, that means we are increasing the turbulence, so the flame speed increases. Another way of looking at this flame speed is people talk about burn angle. So, this is another parameter that quantifies the angle through which the crankshaft turns during the flame propagation mode. So, typically it is 25 degree ignition, 25 degree, that means 10 degree ignition at 10 degree before TDC and complete combustion at 15 degree after TDC. That means total propagation period is about 25 degree. The increase in the angle of ignition and flame speed flame development period is mainly due to constant spark ignition process in the real time. If you look at this Born angle plot with engine speed, when there is about they rise in a very steady manner, and roughly you can say when you are going at higher speed, the Born angle increases. So, Born angle also is less when we are at lower engine speed. So, this is also needs to be controlled. And the last part of our the mechanism process in SI engine is flame terminations. So, I mentioned earlier that flame is going to be terminated for two reasons. First thing, that the rate at which the flame is moving in the beginning drops when it is towards the end of the piston phase, or when it is close to the region of piston phase. So, why? Because first thing, we are going to get the strength or the richness of the mixture comes down. That means, the flame has done its job in combusting all the air fuel mixture which is supposed to do, number one. Number two is that on this piston phase, what happens, whatever heat is getting released on this piston phase, and this heat, it is going to be absorbed because they are metallic surfaces. When it is absorbed, that means the flame does not have sufficient strength or heat to move further. That means reaction rate gets reduced. So, when the reaction rate gets reduced, flame is likely to be extinguished. So, this is the main basic reason that why a flame is going to terminate. There are two reasons. One is stagnant boundary layer dampens the induced turbulence of gas mixture. Secondly, metal walls, that means here the metal walls refers to the piston phase, acts as a heat sink and conducts away much of the energy being released in the reaction flame. Now, if at all we need to do the combustion chamber design such a way that the piston pressure cylinder pressure tapers away should slowly to a 0 value during flame termination mode, and also we need to ensure that fuel should not self ignite at the end of the combustion that means fuel should not self ignite. So, self ignition should not occur, and during this and for smooth operation of the engine, we need to have maximum power which needs to be generated. So, this is how the entire philosophy that we need to get is the fact that a smooth pressure crank angle curve has to be ensured in deciding the flame front speed. Knocking should not occur, the fuel should have sufficient self ignition temperature, so it should not self ignite. So, all these things needs to be ensured. Now, let us move on to combustion mechanism for CI engines. The combustion in CI engine is quite different from the SI engine. So, it is mainly due to the fact that here the mixture is a heterogeneous mixture, and the other aspect is that the combustion happens in a constant pressure mode, which is unlikely, not possible in a constant volume mode. So, it is a constant pressure based combustion and operated through a diesel cycle. So, it is a constant pressure. Why it is constant pressure? Because the pressure can remain constant, or we can regulate the pressure by controlling the fuel injected per cycle. So, by this is in our hand, by controlling the fuel injection we can control this the constant pressure process. Other aspect is that when you look at the pressure volume diagram, we have a pumping loop and we have a power loop. So, basically this is a power loop and this is about pumping loop, and this pumping loop or pumping power can be reduced by controlling the amount of fuel injection period. So, in that sense we can say it is a CI engine is a better approach in terms of increasing the fuel efficiency, because entire things are controlled through fuel injection process. So, here the sequence of events in a combustion process in CI engines has the following features. One is atomization process, vaporization process, mixing process, self ignition process, and finally combustion process. So, this sequence of event is very vital. Now, why we want to have this sequence of event? Now, to have this sequence event, what are the necessity we need to have? So, first thing is that we need to have a very high compression ratio, that is in the range of 10 to 24. So, that fuel can self ignite. Now, in order to have very efficiently injecting the fuel, or in order to have efficient combustion, the equivalence ratio should not be less than 0.8, and the fuel should be injected late into the compression stroke by one or multiple fuel injectors in each cylinders, and this injection and this injection process should be about 20-degree crank rotation. That means, starting at 15-degree before TDC and ending at 5-degree after TDC with ignition delay fairly constant. That means, whatever the compression ratio you have, based on that we have certain temperature. With that temperature, if you ensure this particular injection process, we will have a fairly constant ignition delay. And here the high injection velocity of the fuel is required, so that fuel can spread throughout and cause it to mix with the air. Now, let us visit one by one of the sequence of event. The first event is the atomization. Here the fuel droplets is injected from the injector and from a nozzle, and this injector is about 0.2 mm to 1 mm diameter, and the velocity of the fuel leaving the nozzle is about 100 to 200 meter per second. The fuel droplet diameter is about 10 micron. The atomization process becomes quicker and efficient if the original droplet size is emitted when the injector is small, and the fuel jets from the injector has different zones. What are the different zones? So, normally if you look at this figure, we have a from the injector when the fuel comes out. So, it is in the liquid phase beginningly. So, we can say this is the axis. So, along the axis, when it goes as a jet, and over the certain period of time it tries to spread. So, while spreading along the axis or central line of the axis, it is in liquid phase and tries to get vaporized as and when it spreads, because it is seeing a very high temperature in the engine cylinder. So, in this way there are different zones A, B, C, D, E. So, these zones are basically it is classified that it is a different regions of the compositions, and because of this region we say it is a heterogeneous combustions, and region A, B, C, D, E, they have different compositions, or what we say either it is too rich or too lean, or rich and combustible, lean and combustible, and too lean to burn. So, accordingly we have classified as A, B, C, D, E, but this is not so when we are viewing the combustion in the SI engine. But however, when you say the combustion has to be initiated, it has to be initiated at a location mainly when the fuel is rich and combustible. So, particularly in the region B. So, it starts with B, and so we say it is a, that means locally or it can be a lean and combustible, that is D. So, we can say this could be the zone at which the fuel at this zone should self ignite, and that means they are locally homogeneous in this region B and D. Now, when and as a result it try to self ignite the different layers of the fuel sequentially. Okay, so that is a different aspect. So, we see that this is about the atomization process. Now, the vaporization process happen, these small liquid droplets that gets injected try to gets vaporized, because it sees a compression ratio of 12 and the temperature is also high. 90% of the fuel gets vaporized during first millisecond of the injection, but when the fuel is evaporates, the immediate surrounding is cooled by evaporative cooling. So, it affects greatly the subsequent evaporations. So, in that is the reason we require continuous mixing, so that this particular at any point of time we should not, the flame or the flame generated in this region should not be extinguished. So, we require additional mixing or heating for subsequent fuel evaporations. The next segment is about mixing. So, in this mixing process, the fuel vapor mixes with air to form a combustible mixture within the desired equivalence ratio 0.8 to 1.8. So, the mixing mechanism adds swirl, turbulence of high fuel injection velocity with air in the engine cylinder, and it is a non-homogeneous distribution. Then here the self ignition starts, and this when the self ignition starts. So, this occurs typically for CI engine about 8 degree before TDC, that means 6 to 8 degree after the start of combustion. The actual combustion is preceded by secondary reaction, so including breaking down of large hydrocarbon molecules into the smaller species. That means, if you can see diesel engines contains large hydrocarbons, they have to the molecules should be brought down through this oxidation process. The reaction caused by high temperature are generally exothermic, and because of this reason we can say the rise in the temperature. So, here in a similar way the diesel engine combustion is viewed also in a pressure crank angle diagram, but here if you can see there are three important distinct zones A, B and C. So, A is the location at which the fuel injection starts. So, you can say this location as the crank angle in terms of BTDC or ATDC. So, AB is falls before TDC. So, A stands for fuel injection starting, B stands for ignition to occur. So that AB becomes ignition delay, and at C the fuel injection stops. So, we can see in this process initially there is a the slope of this line AB is little bit slow, but from B to C it is a sharp rise in the pressure. So, this what we see in a typical SI engine, CI engine curve, and in fact this is a completely different process in terms of rise as compared to SI engine. Then last part, which is the combustion process. At this stage 70 to 95% of the fuel in the combustion chamber are in vapor state. There is a non-homogeneous air fuel mixture of different region A to E, and they have equivalence ratio from 1 to 8. The combustion starts through self ignition simultaneously at multiple locations. At many locations it can happen, because these zones B and D you can have here, you can have here. So, there may be many locations which are similar to B and D in this vicinity, where we can say that the self ignition can start at many locations. So, because of this also there could be a multiple flame spawns that spreads from many self ignition sites, and they consume all the air fuel mixture. and because of this self ignition and rise, it produces a quick rise that is noted from between B to C. So, this rise is noted because of the self ignition at multiple locations in the domain. Something more about this thing, what you can say, the combustion normally lasts about 40 to 50 degree crank angle engine rotation, which is much longer than the 20 degree of fuel injection, and it may extend to power stroke also. So, many engines also try to see that fuel injection process they keep on doing towards the power stroke also. The average engine speed strongly correlates with the inverse of the stroke length. The average piston speed is about 5 to 20 meter per second. Now, this to ensure this average piston speed, the pressure rise should be correlated. The most important factor for this CI engine combustion is that we need to look at the C10 number. So, if the C10 number of the fuel is low, greater amount of the fuel should be injected, and so during the ignition injected during ignition delay time, so that we can have a self sustained mode of combustion. In such case, but the additional fuel will cause the pressure at the point B to increase at a faster rate. So, resulting rough engine cycles. So, basically if you do not just to bottom line is that if you do not use a ideal value of C10 number for an application, we need to give more and more fuel, and when you give more and more fuel, the rise in pressure also will be very faster rate, and this rise in pressure also gets felt during the expansion stroke, and if at all the knock has to happen, the knock will happen during this period if the C10 value is not adequate or it is too low. So, this is all about the combustion in CI and SI engines, but there is some limelight or some important things that I need to emphasize in a CI engine in particular, which we call as a direct injection or indirect injections. So, direct injection means that we see that the fuel goes into the engine cylinder directly, that means through either by the spray or by any mechanism. So, it is being injected into the compressed air directly in the engine cylinder. So, this is possible, and normally the large engines they have this particular direct engine concept, but they run at slow speed, and in that case, and we also ensure that there needs to be a finite value of crank rotation, where the entire process of events from atomization to combustion has to be completed. And if the engine cylinder size is small, with that same rotation it is not possible to carry out all the events. So, for that reason, when you are using a large engine, we can somehow manage these things. So, the large open combustion chambers can manage this without the need of any high swirls. So, such engines are called direct injection engines, and this is, and also there are other requirement that for the direct injection engines we have a low combustion chamber surface to volume air ratio, we have a very reduced friction losses, and they have very higher brake thermal efficiency at slower speeds when you have this. And to achieve this, we require a higher compression ratio. But what happens when you are using a small engines, we do not have sufficient time to perform all the events. So, for that reason we require a secondary method of injections. So, that we call as a indirect injection engines. So, for that the indirect injection engines had provisions of divided chambers. Instead of single combustion chamber, they have multiple chambers with a provision of secondary fuel injections. So, these engines can operate at lower injection pressure and lower fuel velocities, and this has to be done so as to map the 40 to 50 degree engine crank rotation, we can map this. That means, to map this we need a faster flame speed, which has to be 10 times faster. To do that, we have to do multi point injections, and here we call them as a indirect injection engines. Okay. So, this is all about the combustion process in engines. Now, let us solve some numerical problems. So, based on this particular combustion. So, here we have studied combustion in SI engine and combustion in CI engines. So, the first problem talks about the combustion process in an SI engines. So, the question is that the spark plug is fired 18 degree before TDC in an engine running at 1800 RPM. So, the somewhere we can say, if you look at this diagram, if this is your TDC, the spark occurs something about 18 degree. It takes about 8 degree of engine rotation to start the combustion. That means, from this point spark, so it takes about 8 degree to start combustion and get into the flame propagation mode. The flame termination occurs 12 degree after TDC. Now, what you require is the flame speed. To have this flame speed, we require if you say flame speed BF, something about distance by time. Okay. So, distance, for the distance it is saying that the bore diameter is 80 mm and the spark plug is located 8 mm offset from the central line. So, if you see central line of this cylinder somewhere, and this is your bore, and spark plug is somewhere 8 mm from the central line. Then, so we can say distance would be bore by 2 plus 8. So, bore by 2, 80 by 2, 40 plus 8, 48 mm, and the spark plug this is about 18 degree BTDC. Combustion start degree crank rotation. So, this will implies 18 minus 8, 10 degree BTDC. Flame termination 12 degree, 80 DC. So, we can say the flame propagation period should be that is 10 degree BTDC plus 12 degree 80 DC, that is 22 degree engine rotation. So, means flame propagates 22 degree of engine rotations. So, now you have to express in terms of this time. So, time can be calculated for this angle. We can say 22 by 360 revolution divided by engine speed is given 1800 RPM. So, 1800 by 60 revolution per second. So, this time can be calculated as 0.00204. So, the flame speed can be calculated as D is 48 divided by 1000 divided by 0.00204. So, this turns out to be 23.5 meter per second. So, this is a very reasonable number that of a flame speed in a SI engine. Okay. So, next question is in line with the first question. So, you take the data from the question 1. What has happened is that engine speed is increased to 3000 rpm, and when it is increased, so obviously the turbulence or swirl gets increased and the flame speed also increases, and finally it is at a rate 0.85 times the engine rpm. So, first thing that we need to calculate that at this particular speed, what is the engine, what is the flame speed. So, you should recall the first question data for which we have N 1 is 1800 rpm. Now, N 2 becomes 3000 rpm in this case, and that point of time we have Vf 1, we can say 23.5 meter per second, and here the Vf 2 we can say it is proportional to 0.85 times n. So, this can be calculated as Vf 2 by Vf 1 0.85 times So, from this calculation we can get Vf 2 would be 33.3 meter per second. Okay. So, Vf 2 you got, but what the question was asked at this point, the flame development of the spark plug firing is takes about 8 degree of crank rotation. Calculate the advancement of ignition timing for flame termination to happen at 12 degree before TDC. So, that means keeping all the data same, we need to say that how much advancement of ignition timing we should make. So, again also after having this, so we should first find out what is the time. So, time would be distance by Vf 2 or that is revised flame speed. So, distance remains as it is 0.048 as in the question 1 by 33.3. So, this turns about 0.00144 second. Once you get timing, then we can say find out theta. So, corresponding theta would be 360 into this time into n. So, this number would be n is in this case is 3000. So, 360 into 0.00144 into 3000. So, this is about 25.92 degree. So, this is the total flame propagation period. Flame termination (12 degree) 80 DC and 8 degree start of combustion. So, the flame propagations to start. So, propagation we can calculate from this data. So, this has to be 25.92 minus 8, that means 13.92 degree at before TDC. Then the spark plug should be fired this 13.2 degree plus 8 degree, that is the start of combustion. So, this should be start at 13.92 plus 8, that means 21.92 degree before TDC. Okay. So, from question 1 data we have the spark plug firing which is 18 degree before TDC. So, this means spark advancement of ignition timing, that is 21.92 minus 18, that is 3.92 degree. The spark must be advanced by 3.92 degree crank rotation. Okay. So, the last question is about this diesel engine combustion, where data is given that it is given with a compression ratio 18. It operates at 2400 rpm. Fuel injection starts 20 degree before TDC, combustion starts 7 degree before TDC, combustion lasts for about 42 degree crank rotations. Now, we have to calculate two parameters, ignition delay and fuel cutoff ratio. So, it is a straightforward solution, because we know three data: fuel injection, this is 20 degree BTDC, start of combustion, so this is 7 degree before TDC. So, this will give you ignition delay about 13 degree crank rotation. So, this 13 degree will imply how much time? 13 by 360 revolution divided by engine speed 2400 by 60 revolution per second, and those, so that ID, ignition ID becomes 9 millisecond. So, we got the first answer, what is the ignition delay. Next question is that what is the value of fuel cutoff ratio? Fuel cutoff ratio if you look at this dual cycle data, constant volume and constant pressure. So, fuel cutoff is this distance. So, it is BC by fuel cutoff ratio is defined by beta dot B by B TDC or B by BC clearance volume. So, this particular expression we can say, so recall your engine kinematics. We have one relations of beta as a function of compression ratio, as a function of the combustion angle, and as a function of crank offset. So, that relation we can recall as, that is nothing but 1 plus 1 by 2 RC minus 1 capital R plus 1 minus cos theta minus square root of R square minus sin square theta. So, this is the expression for beta, that is nothing but fuel cutoff ratio. So, here data given, RC is given 18, theta is given combustion lasts for 42 degree crank rotation, but actual combustion should be, start of combustion is 7 degree. So, theta will be that, here theta remains is called combustion angle. So, it is 42 minus 7 is 135 degree. So, theta is known, RC is known, and we have crank offset R, that is given as 3.8. Okay. By putting this value we can get beta as 2.9. So, this is nothing but your fuel cutoff ratio. So, this is how the question on diesel engine combustion is solved. So, with this I conclude the discussions for today. Thank you for your attention.